Today I'm going to start the bulk cavitation. Bulk cavitation phenomena, in general, cavitation phenomena is the most important phenomena for surface, the air-water interaction as a result of fluid surface effect. So, which I want you to pay really attention. When you solve any surface ship problem, this phenomena always come into picture. I didn't explain, I talk about the rarefaction wave, which is, I said, the tension wave and all that, but I did not getting into detail. But this week, I'm going to get into detail, make sure everybody understand, then is a very good thing. Without cavitation, definition of cavitation and its effect, you can explain like why China naval ship break into two pieces. With understanding of this, then it's very easy to follow the damage process and so on, okay? And what I did last Friday was like this. And this is intersection point O. And you have incident shock wave, which is the alpha. And of course I said acoustic velocity in the water is a C naught. I just picked the acoustic velocity in the air as a CG, okay? It could be oil. Application-wise, if you change oil, it's oil-water interaction problem you can apply to the gas explosion too, okay? Then you can add fire and temperature change in air, in the oil or water. So there are a lot of different factors you can apply into it in alpha. And here this is reflection wave. This is the incident shock wave. This happened to be alpha prime. And this is, I said, free surface. Then, of course, shock wave or acoustic wave will transmit into the air, right? That transmit into the air. So we put transmitting wave. This is alpha double prime. Sometimes, as I recall, I use alpha G, but it's all the same, okay? So alpha prime, alpha double prime. Then we derive Snell's law. Snell's law is derivation is based on the defining the surface velocity. So when you do that, what we have was C naught over sine alpha is equal to C naught sine alpha prime. This is alpha, and which is equal to CG sine alpha double prime. So each quantity is really right at this point due to the incident reflection transmitted the wave. This is, if you compute the acoustic velocity along the surface, that's what this is. And C naught over sine alpha, this is larger, value is larger than C naught. Well, divided by sine alpha. Alpha max of the sine alpha is 1. So otherwise it's below 1, which means C naught over sine alpha is higher than C naught, right? So this is the one thing is Snell's law. And if you equate it from here to here, you can say alpha is alpha prime. And from here, you can express, well, isn't the second term is right here. You can define from here the alpha prime. You can determine the alpha prime. Alpha prime, I want to stick in your mind that alpha prime is always small, because as you will compute coupled sample problem, impedance in the air is much smaller than impedance in the water. How much smaller? What's the ratio? What's the ratio? I didn't ask you to memorize it, but something like C naught, rho naught, C naught. CG is approximately 3600 difference, because density of the air is much lower than the density of the water. So this is called called impedance. This impedance, some people call it, of course, characteristic impedance, but impedance is impedance which characterized media, water media and air media. From here, of course, C naught is about 4.5 times higher than the CG. Okay, this is so basics. If you ask me, do I have to memorize it? I will say stick them in here. So basics, okay? So nothing much. And we did all this. And Friday I assigned homework to derive this two equation from this relation, from that, using equation 1, 2, 3, whatever, then P plus P prime is equal to PG. So right at this point, consider right at the intersection point right there. So third one equation is P plus P prime is right here. In front of incident shock wave, P naught, behind is a P all the way around here. And behind here is a P prime. So of course right here is always P. So this is equal to here in the air, which is PG. Using that relation, with all the relation up there, you should be able to, 1, 2, 3, 2 is here. You should be able to derive this relation, derive it, okay? Correctly derive it. Do it in an hour. You don't need more than an hour. Maybe 30 minutes or maybe 15 minutes, okay? It's a due Friday because it takes about an hour. So anyway, Jong-ho missed the lecture today, but he was here Friday, so it shouldn't be a problem. And I said, let's replace, this is a water in this equation, this is the air, this is a water. Interface is here. So using this equation set, can I derive the relation for the case rigid, the water situation? So to do that, if this is a rigid, rho z Cg impedance has to be infinitely higher, greater. So let's assume in this equation, assume impedance of the air is really higher than impedance of the water, right? Then if I do that, then which means I can assume this is a rigid boundary and the water. We have equations done for that case, so this should converge to that result, right? So if you do that here, so what I see, I'm going to divide this equation up and down by rho g Cg. Okay, look at carefully here. I'm going to divide it. So this is now 1, and this is a 1, and now this term becomes rho naught C naught over rho g Cg. Then if this is large, this term converges to, if I divide everything up and down by rho g Cg, this term is simply cosine alpha minus rho naught C naught over rho g Cg, which is equal to 0, right? Because we are going to replace for the case rho g Cg is really higher than rho naught C naught, which really means rho naught C naught over rho g Cg is approaching to what? Approaching to what? 0, right? This is very high, right? Compared to this. Then I can say this approach to 0. That's what using these two equations we are going to check out for the case of the rigid and the water interface problem. So this becomes 0, right? And for this case, if you divide by rho g Cg, this is cosine alpha here, then this term goes to 0, right? So this term 0, this term 0, so remaining term is cosine alpha over cosine alpha, which is equal to 1, which means P prime is equal to P, right? Reflection wave pressure is same as incident wave pressure, shock wave pressure. And U prime is equal to U. That's what the rigid, the boundary with the water situations is, right? And down here, you divide the same thing up and down by rho g Cg, then this is a 2 cosine alpha. So now this term is simply cosine alpha. This term goes to 0, right? Don't you? So which means the remaining term is cosine 2 cosine alpha divided by cosine alpha. Cosine alpha cancels up, is only 2. Pg is equal to Pg over P is equal to 2, which means Pg is equal to 2P. What's the Pg here? We assume this is a rigid. So Pg is the pressure experienced by the rigid point, right? Right. Assume this is a rigid, right? So, which means when you have a shock wave coming, hit the rigid wall, right? This guy experienced twice of the incident shock wave pressure. That's what that is. So that one, and this is a 2 is equal to this term here. So I'm gonna move this term, rho g cg over rho naught c naught move here. Then what happened? That's equal to 0. So which means ug is equal to 0. What's a ug? Ug is the rigid body, rigid surface boundary point, which is rigid, no motion. So ug has to be equal to 0. Then these equations give you ug is equal to 0. So this equation is a really beautiful equation to work with for the free surface problem with the air and the water situation. Not only that, other situation you can apply to.
위의 식에 따르면 로제로 시제로가 3,600 크다고 나오는데 저 밑에서는 리스트 바운드리 로제로 로지 CG가 훨씬 크다고 나오는데
이거는 어느 케이스야? 이거는 무슨 케이스라고 그랬어? 이거는 제너럴한 케이스지, 그지? 근데 이거는 it can be easily verified that for the rigid surface, 이게 이거보다 엄청나게 큰 거지. If you replace the air by rigid surface, 이 에어를 이렇게 아주 rigid한 그런 surface로 바꾸면은 우리가 저 처음에 solve했던 the rigid surface boundary and water interface problem. 왜냐하면 이 안반의 바다의 바닥이 안반이고 물이 있을 때의 결과하고 이 이퀘이션을 사용해서 똑같이 solve할 수 있어요. 해답이 같아야지. This is the if. 영균아 무슨 말인지 알아? 3600배는 that's real. Air and water impedance ratio is 3600. 응? 알겠어? 근데 지금 무슨 케이스를 생각해 보냐 하면 에어를 rigid로 바꿔보면 그 결과가 우리가 solve 했던 그 결과하고 똑같이 나오지 않을까 이 말이지. 어려운 거 아무것도 없는데? You have any difficulty to understand? 영현.
이 위에 식들 있지 않습니까? 이거는 에어에 관한 식이구나.
이 식은 지금 우리가 뭐로 지금 드라이브를 한 거야? That's a good question. 여기 보면은 이거는 이거지, 이 케이스. 이 케이스를 하는 거 아니야? Reflection of acoustic wave at the free surface, air, water interface problem. 이 문제를 solve한 결과지. 응?
저기 식 좀 전에 드라이브 할 때 저기에서 요나 시나시 요지 시리보다 지금은 큰 경우 아닌데 이 식 드라이브.
이거는
아니 위에 지금.
응? 요거는 characteristic impedance of air. 이거는 characteristic impedance in water. 이거는 그거야. 이건 지금 밑에는 이 식을 우리가 we derive this equation based on the air-water interface problem. Then now Well, question is, can we use this equation set to solve the problem for a rigid boundary with the water in it? Rigid boundary with the water. Can we solve using this equation set? This is air-water interface problem solution. This. Why? Because it's alpha double prime is a transmitted wave angle, right? You follow me? Don't confuse. And by using these two equations, can we see the solution for that problem? If I replace the air, the impedance is very large, okay, then you should converge to this. Impedance is really showing the characteristics of that media. Nothing to confuse here. Chuid, confuse it? Nothing. Abdullah, do you follow me? 경석, 이래? I didn't do anything. This is up to solving. This is a solution for air-water interface problem. Now from here, say, well, we have this, we get the solution, you will derive the solution. Then using this equation set, can we try to get the solution for rigid boundary case, which means replace air by rigid? That means rho g Cg is very high compared to the water impedance. That's about all. Then that's what we used here. So rho naught C naught over rho g Cg. Rho g Cg is very high. Then rho naught C naught over rho g Cg approach to 0. That's all I said here. I'll put this in the final exam. Make sure you understand. Okay, this is what the result of the after I set the rho naught C naught over rho g Cg is equal to 0. Okay. So now, as one example, let's set incident shock wave pressure is 1000 psi. Whatever, you can have a megapascal. Then alpha is equal to 45 degree. Shock wave is coming about 45 degree angle, coming this way. Then you can just use that two equation. Ratio of sine alpha prime, alpha double prime is this. Then alpha double prime transmitting angle is about 9 degree. 9 degree is some angle there. And ratio of the impedance is 3600. You know, as a very good approximation. And PG over P is, if you compute that, is right here. Watch here. 현철, watch here. Very small, which means PG is equal to that constant value multiplied by P, which is 0.4 psi. PG is 0.4 psi. What's a PG? What's the PG? PG is shock wave pressure transmitted from water to the air media. You have 1,000 psi, you have 1,000 psi incident shock wave pressure coming to the free surface this way, then the amount of the pressure escape into the air is only 0.4. 0.4 psi out of 1,000 psi. What's the air pressure? 1 bar, which is 14.7 psi. For 0.4 psi, you don't feel. You do not feel the shock pressure escape into the air. That's what I'm telling. What I'm telling here is you are pretty safe when you conduct the underwater shock testing. You can stand in the shore, not in the water, away from the shock testing site point, then you are still safe because shock wave escape into the air is almost nothing. You follow me? Say yes, yes. Okay, but you don't get the shock. However, it will generate the plume. Then if in a windy day, the plume goes up very high, sometimes 25 feet, 50 feet, depend on the charge size. When it shoot up, then when wind blows, you will get the black shower. All black stuff. All the TNT, all that stuff is black stuff after explosion. And compute the rest of the quantity on the UG. You have a U is about 200 inch per second. UG is 285. UG is really, you can say, air particle velocity right at that point here. Okay? Which is, if you look at carefully what that is this guy, U is equal to 200, is fluid particle velocity in conjunction with incident shock wave. U prime is up here, which is 199.9, and for the vector sum, that's the UG, okay? And P prime is reflection shock wave pressure behind the reflection wave, which is negative 0.9996. So if you multiply P to this, P prime is a negative value, negative, because there's a tension wave or rarefaction wave. Okay? So that's what all. So I want you to go through once again in your leisure time. So this is what the UG here is. Okay? And the surface effect. Surface effect is as shown, as you see here, and the fluid particle right here is shooting vertically up, because this is incident due to the incident shock wave. This is fluid particle velocity right here due to the incident shock wave. This guy is due to the reflection shock wave, and the fluid particle right here try to move in that direction, at the same time move in that direction. So resultant velocity vector is almost vertically upward direction. So if you assume this is a CG of the naval ship, any surface ship here, if this is a CG, then at the time of explosion, that surface ship, after shock, it will always try to move in vertical direction, which is called the kickoff direction. This velocity is called the kickoff velocity. You can assume as approximation this is CG, or depend on, for naval ship or surface ship, CG could be below the surface ship, but still close to the surface ship, like a DDG class ship. The draft is something like, as I recall, some 20 feet. For a PCC class ship here, should be less than 5 feet. Very close to free surface. So you can say still the kickoff velocity is always vertical. Even if explosion occurs here, way out there, still the surface ship will kick off in the vertical direction due to the tension wave or rarefaction wave. Okay, that's very important fact. And that's what the surface effect. I want you to read all the small wording. And cavitation always occurs near the free surface, okay? So next section is what? About that one. And this, you don't have to worry. This is really approximation. Nowadays you can compute exact, so you don't have to use approximation. But this is approximation when R is very large, far field explosion, but you don't have to do that, okay? And this is a terminology about the reflection wave and transmission wave, diffraction, scattered pressure. Scattered pressure is really wave generated due to the motion of the boundary of any target. For example, compression wave, the rarefaction wave. Refraction wave is same as transmitted wave, okay? Transmit into the soil on the ground at the seabed. An explosion occurs, okay? Surface reflection, incident shock wave. Some will go down to hit the ocean bed, and some will reflect, and some will transmit into the ocean bed under the soil, vice versa. Okay, so wave action is done. So next is real application. When I say application, based on the chapter 2 knowledge, and with lots of experiment done before, mostly in U.S. Navy, there is an empirical formula they generate. That's what I'm going to show you on this. And this equation is really first equation, pressure. Think about the pressure. So this is expressing pressure as a function of Pmax, and theta, of course, T. Theta is called decay rate constant. In other words, decay rate means the way how the shock pressure the decrease exponentially depend on the theta value. Theta value is right here. Decay rate curve is slightly different each other. So depend on the type of the charge, then theta value changes, slightly change, not greatly change. So this equation set, I want you to understand fully, this is nothing but the exponentially decaying pressure. That's what the conventional or chemical explosive does, always, okay? Exponentially decaying pressure. So this is a P versus time T. 0 time is a time of explosion, okay? Regardless of where the target is, the time of explosion is reference time, 0, okay? So from 0, then T1, this T1 is the time that the shock wave front touch the target, whatever the target is. So this is like explosion is here. So this is a target point here, let's say. So time it reach to the target point is time T1. So time T1 is if I say this distance is R, so this T1 is equal to R over C naught in the water, right? So then this is a time T1. So T1 target-wise is calm, no shock experienced until the time T1 passed, and at the time shock wave hit the target, everything is calm. So everything is calm. So T minus T1 is shock wave will pass by. So if I say, so what happened after it passes up to here, which is really total time is T. So you have to subtract the time T1 to get the time after shock wave hit the target. That's reference 0. So sometimes people use this T minus T1 as simply T. Okay, the reference time is a time that that the shock wave hit the target right here. So start counting from here. That's fine, because our interest is what happened after shock wave hit the target. You follow me? So theta is a function of the charge type. Okay, so you will see in a minute. So this is everything is all calm until time T1, then bang, then coming down, exponential decay. Okay. So I wrote a small sample right there, right here. This is what the exponential decay curve here. Exponential decay. P max is which is a function of charge type, as you will see. P max here, then exponential decay rate, bang, down here. And this point, this is the point where I set T minus T1 is equal to theta. Theta value is about 2.81, let's say 3. And this point is about the 1/3 of the P max point. I put the red dot here. Strictly speaking, the from here to here is you can really assume the shock wave pressure is up to here is good. After this is so-so. But in the prediction, I use just all the way down as is, okay? And it could, the slope could come this way, maybe could come this way, but there is no guideline. You can assume theta, you can use the same theta all the way down here. But with understanding up to here, it matches better with actual experimental result. But doesn't matter, just you can use all the way to the end. And this is empirical formula. P max is a function of the charge weight. This is all unit dependent. W, they use a pound force, it's a force. And R is stand of distance, the distance from the charge point to the target in feet. This is a feet, this is a pound, then this is a PSI, because this is originally developed in US by US Navy. In Europe, they convert into the metric. Korea, you convert into metric too. That's what we are using it. Theta is again the function. K1, A1 is the value dependent to the charge type, okay? For TNT, some value. You have a table coming in a few pages down. And for the decay constant is in this equation. K2, A2, that's charge type dependent constant value. W, charge weight. R is a stand of distance, okay? And showing the example to get some feel. This is HBX1. HBX1 charge is about 50% strength-wise, so 50% higher than the TNT. Let's say 250 pound charge, and 20 feet is a stand of distance. Then let's look at initial peak pressure, okay? So look at the initial peak pressure is about 6,000 psi. 6,000 pound per square inches. Tremendous shock. This is a tremendous shock, okay? And if you hit by that much shock, the target will just fly away, okay? So 250 pounds. Theta value is usually always in terms of a millisecond. T1 is 4 milliseconds. So you can compute all the parameters. And T minus T1 is 0.5 millisecond. That T minus T1 is the time after hit the target. Right? So in that case, is about 2,000 psi, exponentially decaying pressure. So as the stand of distance is moving farther, pressure, excuse me, shock wave of pressure reduces extremely fast. Okay? So, and overall equation, energy is P times velocity dt. This is a distance. So energy is pressure multiplied by distance per unit area. So that's what this equation. But it has all converted into the empirical equation for energy equation. This is all empirical equation. Pound inch per inch cube means per inch square per inch. You can look at that way. Shock wave impulse is area under the pressure, time history, things like that. Okay, I think the parameter wise that's about all you need. So the bubble behavior and the bubble pulse loading. I mentioned about the gas bubble. Right after shock wave propagate in the radial direction, right? Then of course it generates a gas bubble due to the remaining TNT powder surrounded by the water. So it has energy about usually say 48% or 47% of the total energy still trapped in the water. Then it formed the gas bubble, then expand and move in the radial direction. Okay, then it go move out there, then it shrink and coming back down to minimum volume, then lose balance and collapses. When something collapses, second shock wave occurs. That's what the gas bubble pulse is. And depend on the depth of the charge, it can oscillate maybe once or twice or 3 times. Then it migrate toward the free surface. Eventually, when it reached the free surface, it just went out eventually. That's what the process we talk about that. And please read all this. It's nice to, I summarize all this, you can read. This is empirical equation for a max here is a maximum gas bubble size, initial gas bubble size, which has highest energy trapped in there. So after that it shrink down to min, collapses, get back out. Second bubble size is of course smaller than this bubble size. And 33, we talked before, this is the hydrostatic depth equivalent to the air pressure, atmospheric pressure. And D is unit dependent. This is the charge depth. This is a charge depth in feet. And this is oscillation period. First period of oscillation, T is a time that gas bubble grows to max and down to the min. That's a 1 period. That's what the T is, okay? Not the half period. 1 period, move to the max, down to the min, then that's what the time, 1 period of gas bubble. And this equation said this up to here is true, but this is kind of the trivial, then you don't have too much worry about this. But total energy of the charge is, let's say, 100%. Then initial shock wave carries 53%, and the gas bubble carries about 47%. So shock wave carries about 53% out. Then gas bubble has still lots of energy to give a full damage. And this portion is really for the remaining energy, how it goes by. Some will lose, some energy will lose of course in the water, and some will radiate and contribute also for the second bubble, things like that. You can consider really up to here, which is more form. But this is really trivial, okay? Please read this small paragraph. Small paragraph, like the last paragraph, has a meaning in there, okay? Summarizing shock wave equations, P max, theta, decay constant, I is impulse, E is energy, and the gas bubble period, first period, and this is A max is maximum bubble radius, which is the first bubble. And here is, I just pick up the 4, the charge type, which is HBX1 TNT. TNT is a standard charge. You can always compare with the TNT. What's the strength of HBX1 compare with the TNT? PTN compare with the TNT. And nuke is nuclear. And this constant is good, very valid for nuclear, but we are not going to concern about it. So this is what Pmax, this parameter, that set of the parameter. This is a really very good table. It's all unclassified constant, okay? Okay, this is the section 3.2, and 3.3 I'm not going to do today. 3.3 is bulk cavitation. And bulk cavitation, if you look at your note, it has 2 sections. One, I didn't show the derivation of a bulk cavitation equation set, which I want to let you really read sometime as you have more interest into it. And otherwise, I'm going to use two sections you have. One is bulk cavitation derivation. Another one is without derivation. Then move on the application part. That's what you see it there. And I'll stop right here, 10:54. And this is already December, isn't it? So December is short. I'm going to really see how it goes by up to section the 5.2. Then we'll decide whether we're going to have one additional hour of lecture on 14th. 14th is a Friday. But school email, you all saw the school email? 14th is the first day of the exam. But if you have a conflict, I want to see how the lecture goes on. I want to do up to 5.2, and we'll see. Maybe I can comfortably cover up to 5.2 after the Wednesday next week. So 14th is Friday next week, right? Right? I think Friday next week is. So we'll see by next Monday. But we'll just continue to give you a lecture on the explosion. And please turn in your November project to Higyu, whether email or just hand out. Of course, after he collects, I'm going to review them all. And you have a time to come in on 14th, Friday next week. I want to really also see a presentation of gas explosion problem, project, and also one fire project, and 1 or 2 gas explosion project. Do you have? So check out your schedule on 14 for between lecture hour 10 to 11. If you have majority feels I have exam, then we can. But if you don't have exam, maybe we can spend an hour together, even for project presentation. Should you have a time? Anybody has a conflict? You don't have a conflict. Don't look at me like that. So that's a plan. Okay, I'll see you Wednesday.